previously we've seen that force is directly proportional to the product of Q1 and Q2. But is this true for any degrees of separation? Up till now, we've always controlled the degree of separation between the two charged particles. We've always kept it at 4 meters. What about if it's not at 4 meters? Will the same relationship hold, and how will that make things different? So in this investigation, we're going to draw again from the data that we got before, where we kept the distance between the charges constant at 4 meters. And first of all, we varied the magnitude of charge 1 while we kept charge 2 constant, and then we varied the magnitude of charge 2 while we kept charge 1 constant. And we've already seen that when we multiply Q1 by Q2, that product is directly proportional to the force between the two charges. Now what we're going to add to our data in this investigation is that we're going to do the same but at 8 meters separation. So we're going to see how the 4 meter data compares to corresponding data but at 8 meter separation between the charges. And again, we're going to vary what Q1 is, and then we're going to vary what Q2 is. In other words, we're going to vary what the product of Q1 and Q2 is. So what do you think our investigation question is? Be careful, because it might seem that the independent variable in this case is the distance between the charges. Because if that were our first treatment and that our second treatment, the thing that is different between them is the distance between the particles. But in fact, this is going to be 2 investigations running next to one another. So the distance between the particles must come in the context. And the thing that we are varying, as you can see by the sliders, is actually what the charge values are. So what is our independent variable? And then what's our dependent variable? What will we measure as an outcome? We are again looking at how the product of the charges, Q1 times Q2, affects the force between the two charges. But what's different about this investigation is that we want to do this for 2 different separation distances. For separation distances of 4 meters and 8 meters. So our focus question is, how does the product of the charges, Q1 times Q2, affect the force between the two charges for separation distances of 4 meters and 8 meters? So this data is old data that we collected in previous investigations. We had Q1 values, Q2 values, we got the product of the two. And remember, we did collect the data of force, and there is the data. And as you can see, as Q1 times Q2 increases, force also increases. And we plotted this on a graph and we found a straight line, so we know that that's direct proportion. Now what we need to do is do the same, but for 8 meter separation. We're going to use the same values of Q1 and Q2, and therefore of Q1 times Q2, as what we used in the previous investigations. But all of this is going to now be at 8 meter separation. So we open our simulation. We make sure that the two charged particles are 8 meters apart. We measure the distance from the centers. Each grid line stands for a meter. So we can see that from the center of Q1, we have 1, 2, 3, 4, 5, 6, 7, and to the center of Q2, 8 grid lines. That's 8 meter separation between their centers. Now what we're going to do is first we're going to control the magnitude of charge 2 at 200 times 10 to the power minus 6 coulombs, and we're going to change the magnitude of charge 1. At 6 times 10 to the power minus 6 coulombs, the force is 0,2 newtons. 10 times 10 to the power minus 6 coulombs, 0,3 newtons. 14 times 10 to the power minus 6 coulombs, 0,4 newtons. 18 times 10 to the power minus 6 coulombs, 0,5 newtons. 22 times 10 to the power minus 6 coulombs, 0,7 newtons. 26 times 10 to the power minus 6 coulombs, 0,8 newtons. 30 times 10 to the power minus 6 coulombs, 0,9 newtons. 34 times 10 to the power minus 6 coulombs, 1 newton. 38 times 10 to the power minus 6 coulombs, 1,2 newtons. 42 times 10 to the power minus 6 coulombs, 1,3 newtons. 46 times 10 to the power minus 6 coulombs, 1,4 newtons. And 50 times 10 to the power minus 6 coulombs, 1,5 newtons. Now what we do is we control charge 1 at 50 times 10 to the power minus 6 coulombs, but we increase the magnitude of charge 2. First of all, 200 times 10 to the power minus 6 coulombs. We've already got that reading, 1,5 newtons. We increase it to 300 times 10 to the power minus 6 coulombs. The force increases to 2,3 newtons. 400 times 10 to the power minus 6 coulombs, 3,1 newtons. 500 times 10 to the power minus 6 coulombs, 3,8 newtons. And 600 times 10 to the power minus 6 coulombs, 4,6 newtons. We put all of that data into our table. Now what do you notice as you compare the two tables, the 4 meter one and the 8 meter one? It will help us to put them next to one another. So I've taken out the columns Q1 and Q2. We don't need that. We just need Q1 times Q2. So in each case, the independent variable is Q1 times Q2, measured in Coulomb squared, and our dependent variable is the force in newtons. And what do you see as you compare the forces in newtons for a particular Q1 times Q2? If we look at the first line, as you can see, Q1 times Q2 is the same for the two tables, 1,2 times 10 to the power minus 9. But for the 4 meter separation, the force between the two charges is 0,7 newtons, whereas for the 8 meter separation, it's only 0,2. When the charges are closer, they attract one another more strongly than when they're further apart. And you can see that if you compare any two readings. If we take the last reading, we see that Q1 times Q2 in both cases is 3 times 10 to the power minus 8. But for the 4 meter separation, they exert a force of 18,3 newtons, whereas for the 8 meter separation, only 4,6 newtons. So definitely we can see that the distance between the charges affects how strongly they attract or repel one another. But we want to see whether the direct proportion relationship that we found before still applies. Remember that in direct proportion, as one variable increases, the other increases by the same factor. And we can check that two variables are indeed directly proportional to one another by dividing one variable by the other, and if they are directly proportional to one another, that will give a constant value. So we add a column to each of our two tables. And in that column, we're going to divide the force value by the Q1, Q2 value for each line. 0,7 divide by 1,2 times 10 to the power minus 9, and so on. Complete this table before you continue with the movie. What do we see? Check that these are the values that you got when you used your calculator. If these two variables are directly proportional to one another, we should get a constant value when we divide one by the other. Now, if we look here in this column, we don't see exactly the same value all the time. However, you must remember that we have experimental error in this simulation, partly due to rounding off, because the force value is given only to one decimal place, and so our information is not very accurate. So because of that inaccuracy, you have to round off to be able to see the patterns. You have to ignore experimental error. And if you look at these values, you can see that they all round off to 6 times 10 to the power 8. Then if we look at our second table for 8 meter separation, we can see that F divided by Q1 over Q2 always ends up lower than what it did for 4 meter separation. However, if you compare the numbers with one another, again, they would all round off to the same value of 2 times 10 to the power 8. So if we ignore experimental error, we will realize that within each table, F divided by Q1 over Q2 gives a constant value. It's not the same constant for the two tables, but it's the same constant within each table. So here I've rounded the values off so that we can see the pattern nicely. So from this we can see that force is directly proportional to Q1 times Q2 for 4 meter separation, as shown by a constant value here, and force is also directly proportional to Q1 times Q2 for 8 meter separation, as shown by a constant here. When we plot this data on a graph, we find these two lines. You should confirm that this is indeed what we get. You should take the data from the table and draw your own graph. The straight lines which would pass through the origin show us again that we've got direct proportion. The different gradients of the two graphs show us that the constant we get, like we found in the previous table, will not be the same value for the two sets of data, although it will be the same value within a set of data. That's why we get a straight line, because the gradient is that constant. What you need to decide is which of these two lines shows the 4-meter separation and which one shows the 8-meter separation. And then you also need to decide how to complete the heading of the graph and what labels should go on each of the axes. The dark green line is the 4-meter separation and the light green line for the 8-meter separation. The degree of separation can be written as R. How do we know that the dark green line is the 4-meter separation? Because for any particular product of charge, there's a stronger force between the charges when they are closer together than when they are further apart, as shown by the dark green line giving greater values for a particular product of charge than what the light green line gives. The heading is graph showing the effect of product of charge on the force between the charges for two distances between the charges. Product of charge is our independent variable. It goes on our x-axis, the unit Coulomb squared. Force between the charges goes on the y-axis because it is the independent variable, unit newtons. Two distances between the charges, that's our context. And so we have two different series within the graph to be able to compare, well, how does this relationship differ between these two separations between the charges? What is our conclusion? How does the product of the charges affect the force between the two charges? And how is that different for the separation distances of 4 meters and 8 meters? In both cases, whether it be 4 meters or 8 meters or any other distance between separation, the dependent variable is directly proportional to the independent variable in this case. What should go on those lines? Although what is different when we have a different value of the separation between the charges? The force between two charges is directly proportional to the product of the two charges and is greater for a smaller distance separation.